The ocean is a magnificent place, home to a majority of all life on Earth and covering over 70% of the Earth's surface. There's always something to learn from the sea. Definitions of coastline vary, but it is agreed that hundreds of thousands of miles of coastline exist on the Earth. Scientists believe that if all of the wave energy along the coastlines of the world was harnessed annually, it could satisfy the entire world's electricity for that time period. Understanding the ocean could lead to scientific developments in many different fields. However, there is a lack of resources available to provide measurements near the coastline. The Smartfin is the solution to that issue. The Smartfin is a long-bored surfboard fin that is capable of gathering much data through its sensors, including if it is in the water or not, the temperature of the water that it's in, its location, and acceleration. From these sensors, we will be able to produce much other information, such as wave height. With the Smartfin, scientists will be able to gather denser data from many beaches, produce more accurate wave height and water temperature forecasts, find out where, when, and how long people are surfing, and more. Through experiments conducted by the San Diego SRIP pier, we have been able to compare the Smartfin's temperature readings with those of the pier, and also analyze its GPS sensors. In the future, we will compare wave height readings determined by the Smartfin's accelerometer and algorithms to the pier's wave height readings, as measured and analyzed through its pressure sensor.
The data we got from the Smartfin was in an encrypted format, as you can see here. We had to implement a decoder in Python, which was able to produce our data in a table. We also further optimized our decoder by incorporating data analysis methods. Therefore, we were able to graph things such as temperature histograms and temperature over time and GPS sensor measurements. Our Smartfin produces inertial data such as acceleration, gyroscope, and magnetometer. We are currently working on determining the exact position of the Smartfin. In order to get position, we would need to double integrate our acceleration. And along with that, coupled with citizen science, there comes a lot of noise in our data. Therefore, we are implementing a Kalman filter, which uses linear values from our sensors to predict the exact position of our fin. This flowchart right here represents our programming logic, and we hope to add more angular measurements, such as gyroscope data and heading, to our program. So far, we have values for our transition matrices, and we have working code on Jupyter notebooks for these linear values. And we will be optimizing this with process noise, and we will also work on Kalman smoothing in the future.
We are using spectral analysis to determine the wave height from our acceleration data. Spectral analysis is a function that provides information about how power is distributed by analyzing the frequency domain of a function. Our Kalman filter will determine the vertical displacement, which spectral analysis will then process into wave height. Fourier transforms are used to show the frequency domain of a function in the time domain or vice versa. It's very useful for sine functions, which are what we use to represent waves. As you can see below, there is a combination of sine functions expressed as a few frequencies in the frequency domain. We currently have code that is capable of taking CDIP vertical displacement and producing accurate significant wave height graphs. And we are using HM0 as opposed to HS. HS is the average height of the top 1/3 of the waves. HM0 is a little bit more complicated than that. It involves an integral. None of the work we accomplished would have been possible without E4E and our amazing supervisors, Ryan Kastner, Kurt Jurgers, and Nathan Huey. Thanks to their involvement and the help of our team, shown in the picture above, we were able to accomplish much this summer and will accomplish much more in the future. Thank you.